Hello, we are live. We're a little bit early. It is, I think, 1 minute to 2 o'clock in the UK, but this was scheduled for 3 o'clock in Europe, which is an hour different. We have a 15-second delay, but hopefully, if you're on, hear me, then let us know. I'm flying solo today. I have Reese watching this, but if you can hear it, let me know. Yeah, it'll take 15 seconds or so. I have no messages yet. We'll see. So I've got nothing come in, but hopefully it should be live. Maybe it's going to take a little bit of time to start in line with the webinar starting in. Let's go check it. Should be connected to LinkedIn. So it says I'm live. Brilliant. We can all hear me. That's great. Cool. We'll give it 30 seconds before we start. I have a cup of tea that's freshly boiled, a little bit too hot. Cool. 1 minute past and we're in. Should we all start? We should be ready. Brilliant. Okay, before we start, one thing I should say is this is for our customers and our prospective customers. If you are a competitor or you deem yourself to be a competitor of Tucsen, please leave now. This is not intended for you, and we're asking you politely to leave. And if you do stay, then we will take the actions to report you to your HR teams, because this is for our customers. This is our work and our efforts, not to be viewed by competitors. Okay, brilliant. Thank you very much for joining us on a Friday afternoon. I am a little jet lagged. I've just come back from the United States. I flew in and got home about 11:30 last night. But we're going to be good. We're going to have a look today at industrial scientific CMOS, which is a thing I've made up. But anyway, realistically, what we're going to look at is we're going to look at the differences between industrial and scientific cameras and what's in between them. And is there any differences between them at all? That's another important thing. But before we start, we get to do a little advert. So let me move on to the next slide. So that, well, advert for me, just so you know who you're talking to. I'm James Francis. I've been involved in scientific imaging since January of 2000. I'm a director and an advisor at Tucsen Photonics. I'm formerly part of the Teledyne Scientific Imaging Groups, and I was a vice president of Photometrics for many years, creating some great cameras with some great people there. So that's me. What about the company? So Tucsen Photonics was established in 2006. At the top image here, you can see this facility. We now occupy all of that facility as we continue to expand. In fact, we have a kind of probably 2 or 3 squash court size class 100 clean room in there as well now, which is pretty impressive for a lot of the work we do in semiconductor. We've got global sales and support all over the world, including an office that we run out of the United Kingdom, where we do most of our international work from. 220 staff, but really critically, 90 R&D engineers, more than 90. It keeps on changing, with 8 camera teams, meaning we create more than 8 cameras a year and ship over 40,000 units a year. We also produce in Singapore for the US market, and we're also in the United Kingdom, where, as I say, we have my team that's working from there. So what have we got? We've got industrial cameras on the left-hand side, great cameras, don't get me wrong, I'm not going to say anything bad about any of these cameras. And on the right-hand side, we have scientific cameras. And we can make some sort of observations when we look at it about sizes and cooling and fans and formats. But that's what we're going to look at today. And we're going to critically try and work out what would go in the middle. If we're going to have 2 different classes of camera, what are we going to put in the middle? And this is what we have, is industrial scientific cameras, which I'm saying is basically scientific thinking with industrial form. So the right sizes, but having taken into account the jobs that need to be done for scientific imaging. So what we're going to look at, it's a James webinar. James webinars normally have 5 points or 10 points. So today we're going with 5 points. We're going to start off with camera sensor types. So is it a CMOS? Is it a scientific camera? So we're going to talk about the terms that get used and a bit of the story here. And then we're going to talk about the challenges of scientific imaging, like what we as camera manufacturers obsess about. We're going to talk about cooling and heat exchange. Is it liquid cooled? No, it's the heat is removed by liquid. So we're going to get into some definitions here. And we're going to look at what people care about when they're making an instrument. And then finally, we're going to talk about these new cameras. You can see in here, 3 different cameras. Actually, there's like 16 variations of these 3 different cameras that are all coming out from us at the moment to fit into this industrial form. Now, we'll start with the camera sensors. So on the left, we have an sCMOS sensor. On the right, we have a CMOS sensor. And these are called sCMOS and CMOS. You know, the manufacturer of these sensors, both of them come from G-Pixel. They have some definitions to them. They've got some sensors here, right? We would assume that the one on the left-hand side, 95% QE, really, really low noise. And the one on the right-hand side, smaller pixels, lower full well. Well, let's have a little bit of a look at them here. CMOS is a technology. sCMOS kind of isn't. CMOS is complementary metal oxide semiconductor. So this is a type of semiconductor that was invented in the 60s, started being used in the late 70s and 80s when people worked out it was light sensitive as imaging devices. When I started imaging in the early 2000s, these were very cheap color cameras. And my friend Tim, who's no longer with us sadly, used to say, we will be shaking these out of cereal boxes. It's the free gifts that are inside. Anyone born around my era remember those things. But really, by the time we hit the mid-2000s, CMOS was pretty much in most of our lives. We had cell phones with them on. We knew that CCD was disappearing. And in 2009, this term sCMOS came out. And it was to describe a new generation of sensors. It was a description. Let me give you another description. I am young, tall, and handsome. And they are self-defined descriptions, aren't they? I can describe anything. I am a human, that's a technology definition, but actually I can describe myself how I want. I'm a beautiful human, if you like. Now, let's go back into it and start to think a little bit differently. So now we have this kind of scientific sensor and we have an industrial sensor. Just because I've got a scientific sensor doesn't mean I have to make a scientific camera with it. You get lots of people that will take this sensor, put it into a body, and they will make an industrial camera out of a scientific sensor. In the same way, I can take the 3265 from G-Pixel, put it in a scientific body, pay attention to the things that scientists want, and try and make it into a scientific camera. So there's no clear definition of how I'm using sensors. We can both pop sensors into machines. It's just the jobs we're concentrating on that we're going to work with. So let's look up this term scientific CMOS or sCMOS. sCMOS came out, first of all, it was a paper by some really good people at PCO and or Fairchild, which is now owned. The section of Fairchild with made sensors is now owned by Hamamatsu. Really good sensors, and they came out with this sCMOS. And a lot of people were worried about that brand name or trade name, so they started to call cameras scientific CMOS, just to be clear. But if we look at sCMOS as a term and we put it in AI and we say, Google, tell me what you think, it says it's got very low noise, it's very high speed, and it's got wide dynamic range. There's a large field of view and it captures a big area in the single frame. So the quick question here, someone's asked about, is it a bit blurry? We had a problem just before, which is saying that we have to now run it as a screenshot. So we have a little bit of a problem. So hopefully if you bear with it, we will give you the higher res version later on. There's a little bit of text, we'll work around that. But I want to take you back to the story. The story is AI tells you it's very low noise, high speed, wide dynamic range, large field of view. The problem with all of this is that actually I've got industrial cameras and industrial sensors that are very low noise. Sony sensors by default about electron of read noise. So a high-speed camera, you telling me there are no high-speed industrial cameras? There are high-speed industrial cameras with very low noise. Wide dynamic range, I tell you what, industrial cameras have that. Large field of view, so you telling me there are no large format flat panel display cameras out there by industrial cameras? I would argue that there are significantly more large field of view cameras being used in industry. This definition doesn't work anymore. It's a strange definition because realistically, it's not kind of right. It doesn't work for me anymore. And I'll go back here. Now, what we can do is let's play word clouds like word clouds. Let's do a word cloud. If I put industrial camera and say, make me a word cloud out of it, I get all these things: inspection, machine vision, and global shutter, and GIG. There are plenty of scientific cameras with GIG. Industrial global shutter. There are plenty of scientific cameras with global shutters. If I put into scientific and I say quantum efficiency, yeah, that's not important to anyone doing any UV inspection. And I put in low noise, yeah, also in sort of industrial cameras. And dynamic range, also in industrial camera. These definitions don't work, but these are just correlations of words. And the answer to all of this is really very, very obvious. The answer is that they are different jobs, most commonly operating at different light levels, and customers have different needs. It's a different world. So we know we've got these terms. They don't really suit anymore. A camera is a camera, but we've got different needs that are operating on. Let's look at those different needs. Now, baked bean tin inspection. I've been doing this for about, again, 26 years now. And we always used to say, well, industrial inspection is like inspecting baked beans, isn't it? Now, I want you to think about this scenario. I've got plenty of light. I've got a high-speed camera. I don't have the problems that you have. I have all of the wavelengths, and I've got color. If I want more light, I will turn up the light. I'm in a different world. Scientific samples are different, aren't they? They are light sensitive. A lot of them are. They emit a low number of photons. They consistently have multiple discrete signals. They have short lifetimes or dynamic samples to them, right? So, you know, there are things like calcium flashes, discrete signals. Maybe you have red, green, blue. Maybe you have signal there equals no heart attack, signal here equals heart attack. You know, you end up with different things. We've got birefringent patterns, super resolution, spatial biology, light sheet. You've got astronomy, and you've got things like biochips that are working all the time. So we've got different types of samples. And this puts us at the bottom. Most of the time, we're going to be living at the bottom. Now, there are naturally low signals. There's bioluminescence and chemiluminescence and astronomy. These are naturally low photon emitting signals, right? Now, it's not the point of the star in a distant galaxy. It's trying its hardest. It just turns out that the photons arrive here in pretty low numbers relative to our exposure times. But these are naturally low. Most of the time, we create the problem of low light. We create this problem. We have forced low light substance. So we are trying to avoid destroying the sample, or we want to go fast. We want to have a shorter exposure time with less signal in it, so go faster. And for example, in fluorescence microscopy, your desire might be to not photo damage. So you want to use less light, so a shorter exposure time. In voltage imaging, calcium imaging, you might look for a spike or something, and you're recording dynamic events. So you want to get more data points. So you want it to go faster, so you have a shorter exposure time. High content screening, faster, less bleaching, give me the answer quicker. Instrumentation, faster, increase the throughput. Throughput equals more images per second. More images per second equals shorter exposure time, equals more sensitivity. Quantum computing, I want to get that piece of information. I'm not waiting 6 milliseconds for your frame to arrive in the computer. I want to get an answer and change the laser power now. We are forcing the situation of being at the bottom. And these low lights present a problem. Here you go. Here's a bunch of different images. This is Reese created these for me as well. Thank you very much. So we know, let's just guess an industrial camera has, say, 10,000 electrons of signal. If you have 10,000 electrons of signal in your camera, well, look, I do pretty well with 4. So in scientific imaging, my baked bean tin, I can't tell you what, there were no complete saturated pixels, but they're all pretty high up there. But I do pretty well at 4. I can see the image really, really well at 1,000. I'm not doing bad at 100 out of the 10,000 available. To be honest with you, I'm not seeing terrible images at 20. And at 5, I can still see there being something or not. So in this, it's going to depend on how you're using the camera and what you want to get out of it. If I was doing high content screening and I desperately wanted to do something, somewhere between 100 and 1,000 would work. If I was taking a calcium measurement and I wanted to do like a reaction on a plate, somewhere between 20 and 100. If I'm looking for a detection, if I just wanted to say, yes, there was a virus present or not, 5 would do me. It depends, doesn't it? But what the point here is, we're losing significantly lower signals to achieve what we want. Now, remember, there are 4,000 being squashed onto 256 grayscales to be put onto a screen so you can see them. That's a lot of what's happening here. But now we're lower, we're going to be closer to the read noise problem. We have a signal and we have this noise bouncing around. You don't care when it's up here. You care when it's down here and you're bouncing around in the read noise. And this is an sCMOS camera on the left. You can see you've got the Aries, better camera, but you can see that you're going to have problems where you're not going to be able to see structures because of read noise. That's a challenge. Then we get background images. We can see we have dark current increases and we have glows and we have patterns happening inside images. And we have to try to control these things. Don't have to control this when I'm looking at tins of baked beans. These are not functions of baked bean analysis world. We have dark current that's starting to happen. We've got cameras, sometimes they need to be cooled. We'll look at that in detail in a bit. And again, these things are happening because I'm lower in signal. It doesn't matter if I've got dark current. There is always noise. It's just whether or not you see that noise. We got lines. This is even an sCMOS camera, one of the best-selling ones in the world. It's got a load of patterns in it. It's got a load of lines in it, obscuring what you're actually trying to see. You're not going to see these lines at bright light. And if you are doing beam tin inspection, you are happy. It doesn't matter about the lines, nor do you care about these very, very small variations between white and black that happen right at the bottom of the limits. These images sometimes can create, when you zoom in, these problems. If you're taking a picture, actually, if you're just doing an observation, you're fine. But if you're trying to get into the numbers, you don't care about very, very small pixel defects or random telegraph noise. You don't really care about these things. And then we've got bit depth. My apologies, I found this on a website. I forgot to recreate it myself, but you get the idea. What we get here is bit depth. Now, this is a little bit untrue. This is what happens because an 8-bit image can look perfectly fine. It can look perfectly fine as long as we're kind of saturating the data across it. But what I can't do is look at the bottom and then put it into 8 bits. But that's what we'll end up in. And really what I want you to focus on is this limited number of gray levels. How do we get to these limited number of gray levels? Well, I want you to think about a pixel with 15,000 electron full well. Okay? I told you I don't need 15,000 electron full well, do I? But if I looked at it under 8 bits, I have 58 electrons per gray level. I told you there are some images where 100 electrons is fine. Okay? Well, that's not great. If I use 16 bits, I end up with 0.23 electrons per gray, or 4 grayscales equals an electron. Work out how that works later on, but roughly the ratio is how it works. Now, what happens is, if we're only going to use a 1500 electron signal, because remember from the images that Reese took, that was a really, really good image with 1000 electrons. Now, look, I've only got 26 gray levels on my 8-bit camera, and that's why you're seeing that very limited grayscale distribution. But in my 16-bit image, I've got 65,000 levels. Now, again, the 26 is going to be put onto a screen for you in 8 bits, so it's going to look 256, and therefore some of them are just going to be very, very boring grays. My 6,556 levels, they're going to spread out nicely across the 256, so I'm going to look like I have no big steps. And again, if I took it down to 150 electrons, well, my 8-bit camera with my 15,000 electron full well has 2.6. I got 3 gray levels. Now, of course, there's gain. Of course, there's ways of handling this. But this is a fundamental issue in some of the ways that we operate. When we turn on the camera and we go, we don't have the scales. We don't have the nice images. Why? Because we're living at the bottom. What about measurement challenges? I made up some numbers. I have 200 gray levels above bias, which means I have 100 electrons of signal in the world of this camera. 100 electrons of signal equals 500 micromolar of concentration. All fantasy in James's world. But what I want you to do is connect the number of electrons to a measurement that you want to make. Am I sure? The problem with having signal to noise of 100 electrons is I'm roughly going to get a 10 to 1 signal to noise, and I have some uncertainty in my measurement. So 1 divided by the signal to noise is my measurement uncertainty. So I have 10% confidence or 10% uncertainty in the measurement. So for example, if you look here, if I had a signal to noise of 2 to 1, I have poor confidence. If I have signal to noise of 10 to 1, like I do now, I have pretty good confidence. If I have 50, I have excellence. Now, this can be on measuring a line, measuring a circle, making any form of automated measurements. If you're like deeply into, well, how does my intensity measurement change? Because I'm actually worried about that. That then gets into some statistics. So for 100 electrons, 68% of the measurements would lie between 90 and 110. And 95% would lie between 80 and 120. Anyway, you can play with that, but understand that signal to noise is driving a measurement confidence, and it will allow you to actually make the measurements, whether they be single lines or whatever you want, or intensity measurements. You need to understand what you're doing to report the number with confidence. By comparison, my baked bean tin has more than 10,000 electrons. Its exposure time is probably 2 milliseconds. It has 8 bits per color channel. The signal to noise is probably 40 to 1. I am not concerned by patterns, glows, visible pixel defects. Every measurement I'm going to be made is confidence. And if I don't, I just turn up the light. So we can see that scientific instruments live at a lower light level where different problems exist. And because we want shorter exposure times, we're sort of responsible. So now let's look at cooling and heat removal. Do I need a cooled camera? Oh, it needs to be a cooled camera. All these things I've heard over my time, lots of different things. So let's get into it. So the first thing I want to talk about is sensor cooling and heat transfer are different things. And I've heard this a lot. It's liquid cooled. No, the heat is removed by liquid. It's passively cooled. No, the heat is removed passively. It's air cooled. No, the heat was removed by a fan. The air isn't doing the cooling. The air is helping by removing the heat. We call sensors. Sensors and cameras, they go off and generate heat, don't they? If you turn on a camera, put your hand on it, it'll heat up. Brilliant. You could have it in your bed as some form of hot water bottle. We know that. This heat that we know causes electrons to be thermically generated in dark current. I may have 200 extra gray levels because of dark current. I can subtract that. I can take off the 200 if I want. I can't take off the variation of the 200, and that's why I end up with dark current noise. This is exposure time dependent, and it's different for different sensors. So if your camera is cooled by -50, well done. Congratulations. You could get a camera that's cooled by nothing and achieve the same dark current because it's all between the sensors. Dark current halves for every 7 degrees of cooling. Sometimes it does. There are general rules. It's not always the same. It doesn't always work. Sensors are different. So that's the first thing. The other thing that happens is outside the dark current, you get all manner of things that happen that are better behaved when you cool a camera. You get better pixel behavior. You don't have these glows and halo problems as much. Your patterns between the lines, TDI, you will see kind of competitors with uncooled cameras, these big lines between them. Measurement drift over time. Measurements drifting throughout a sequence acquisition. I was recently with a customer and they said, oh, it keeps on going up and down. It's like, yeah, it's going to do that. You've got an uncooled camera, and that's why I was there to talk to them about getting it cooled. I'm not an advocate. I'm an advocate for choice. You have to choose based on the information you have. So I can see these intensity raises. I can see these hot pixels coming up. I can see these glows. I can see these lines. So I cool the sensor. And I can remove the sensors in 2 different ways. I can use thermoelectric cooling like a Peltier device, and I plug it onto the sensor and I cool the sensor. And I'm going to pull the sensor off, and I can get, if I use a TES device, a Peltier device like this, I get active cooling. I can cool below the ambient sensor. I get much lower dark currents. So that's one way of the sensor getting heat off the sensor. The other way is a heat exchange system, right? A heat exchange system. And in this case, hex cooling is pretty popular. Particularly, we do a lot of hex cooling inside our industrial cameras, which are scientific grade industrial cameras, if you like. We want to get down to that. When we do semiconductor inspection with our TDI sensors in very large fabs. Here, there's no Peltier device. Loads of less power. They're silent, and they can work at stable at operating temperatures, but they don't cool below ambient. So I've got ways of getting the heat off the sensor. So why do I want to remove the heat in general? Why do I get it off the camera? I know why I want to get it off the sensor. I want to support the sensor cooling. Let's get it off the sensor. One of the biggest killers of cameras is the FPGA overheating. FPGAs normally have programs in there to turn off when they hit a set temperature of 55, 58, 60 degrees Celsius. You have to protect the FPGA. That is the brain of the camera. You also want to protect other functions. So there are benefits to the camera. There are also benefits to stability, right? You want to drive stability in your instrument. You want to avoid general overheating. You want to avoid an optical shift. You want to avoid your equipment being heated up or things moving because you've got a heat generating source inside your instrument. But where are you making these measurements? So a lot of your cameras will report a measurement. Now, I want you to think about, well, where did that measurement come from? We tend to, at Tucsen, give you 2 different measurements. We tend to give you a sensor temperature and an FPGA temperature. These are pulled by the SDK or reported in any of the software. Some people might give you a housing temperature. Some people might give you an unspecified camera temperature, right? Whatever it is. Think about what you're actually measuring. You might get a number from a camera and you might go, well, yeah, that's the camera's temperature. Okay, the camera's not blowing up and smoking. It's not what the sensor is. So how do we get rid of it? Well, we have non-cooled cameras. What are non-cooled cameras? Well, no efforts made. Might as well be called no effort made to remove the heat cameras. And these basically just heat up the housing, and the housing then irradiates the heat, moves on. And then we can have passively cooled, and in these cases, we put little fins. Why do we put fins? Fins have larger area, suck out the heat floats away. Then we get fanned cooled, where we just blow the heat from one side all the way through the camera. Let's get rid of it through doing that. That's air cooling. And then we get liquid cooling. This way round, we pump through a liquid, not always water, can be, different variations. We also have something called forced air cooling as well. But in this case, we're going to drive liquid round in a little U shape. That's, for us, one single piece of metal, and we run that round so it connects also onto the FPGA because we know the stability of the FPGA is also important. So you're going to go, well, is it a problem for me? Look, both of these cameras are uncooled. Both of these cameras had 100 millisecond exposure time. They're both uncooled. I like the one on the left more than the right. It's going to be totally dependent on the sensor used, your environment, and your signal to noise. Again, let's have a look. Well, what if we didn't cool it? Well, let's have a look here. There's a cooled camera, an uncooled camera has 2 seconds of exposure. I get it. The cooling is helping in the situation. This is the same sensor turned on and off. That's what you're seeing. You're seeing the impact of cooling. So whether it's important to you is like exactly that. It's dependent on your application, right? What's your expected light level? If you took one of our new uncooled cameras we're going to talk about in a minute, and you have 100 milliseconds and you have 100 electrons of signal, you are fine, right? You take another camera with the same light levels, the same exposure time that is uncooled, you might not be fine. So it's going to be down to light level, exposure time, what your target signal to noise is, how bad your target design sensor is, and what impact that camera's heat will have on your instrument. And trust me, that's one of the biggest questions we have. If it's on the side of a microscope, who cares? If it's on the side of an instrument, you care. If so, what type? What type of cooling of the sensor and what type of heat removal do you want? Right, so we looked at that. Let's have a look at what people care about when they're integrating a camera into an instrument, for example. So form, fit, and function. Let's have a look. There are a number of different things. Research scientist mentality is normally driven by, we want the best that we can afford because we don't know where we're going. We don't know if there's longer exposure times. We don't know if there's shorter signals. We don't know if we're going to end up with a signal here and another signal that comes in here and it's saturated. We just don't know. We want the best we can get. That is not true for people putting cameras into instruments. They don't go and want the best, right? You wouldn't give your sales guys a fleet of Ferraris. They are the best. You're probably going to give them something by Ford, right? That's what's going to happen. I want my instrument to be as small as possible. How big is your camera? I want my instrument to not weigh very much. How much does it weigh? I want my instrument to measure values consistently no matter the situation. Can it do that? Is it going to change with temperature? Is it going to change with settings? I need it to fit into my instrument's flow. I want to know about it taking power from my instrument. I want it to take triggers from inside my instrument. I want the heat removal to work in the flow of mine. I have heat removal already. Can it do that? I need to minimize my instrument's bill of materials. How much is it going to cost? Most importantly, it must do the job required. This is the critical thing to an integration engineer. Everything you need and nothing more. And I give the credit to that to James McKechnie. That's exactly what is happening. I need everything I need and nothing more. This is, I do not want to spend more money or have extra functions that I might need in the future. I'm building an instrument. We've already done the thinking. So what are people thinking about when they're integrating systems? They got liquid cooling connectors. Great. Do I want liquid cooling connectors? Okay. Are they going around the FPGA? Because that would be really useful to me. They're going to help with vibrations, obviously, liquid cooling over air. That's kind of nice. Do I have a problem? Could I mount it at the front, remove vibrations? What else can I do? Can I get rid of the things? They're a real pain. They stick out and hook on cables. The software, how easy is it? How easy is the SDK? Can I use it through GennyCam, pick whichever frame grabber I want and program it inside GennyCam, and not your own SDK and be tied to you? What's the digital interface? Is it USB? Has it got a card? How many cards does it have? How many slots am I going to use in my instrument? What are the hardware triggers? These are going to be critical. Camera control. What cables are coming out the back? How big does it become because the cables are sticking out the back? You give me the size of the camera and then stick a cable that comes out like that. Cable that, the cable I could tow a car with. Fan outlet. Does it move the air from the camera in the right way through my system? Could I change it? Which way is the air going? The simple shape. I see these cameras that come out like this. It's like triangles. Cameras need to be square with easy mounting side point holes and as many mounting point holes as possible. Can I choose where the mounting points are? Can I add more myself? Can I mount the camera on the front correctly? What are my options for mounting on the front? What are the distances from the sensor to the focusing rings on the outside of it? Where is the sensor relative to the position of everything? How variation of it? How flat is it? How many angles are coming off it? How repeatable is it? Can I flip the direction of the sensor inside the software so that I can run the camera at full speed in any orientation because I put a mirror in place and now everything's back to front? These are the questions that are happening at an integration level. They're very, very different to the questions that are happening into a research level. So this is where we're getting the industrialized thinking from. The industrialized thinking relates to all of these things. It's not like, okay, I wanted it smaller and cheaper. So let's go into the final bit. This kind of, let's try and wrap some of these things together into this idea of this industrial scientific CMOS. And I said before, industrial scientific CMOS for me, scientific thinking with industrial form. Let's start here. So we have this camera called the Aries 65A4 Pro. It's the world's most sensitive sCMOS camera, a claim I have. Go look at the website when I wrote a paper about it. In each situation, you're going to get different variation, but for most fluorescent signals out there, you're going to get this camera, you're going to get 95% QE and very low read noise. But it's a little bit bigger, so we could make it smaller. I've made it smaller. We made an Aries 65A4 LT, right? A light version of the camera, if you want. It's simplified. We've taken this logic and simplified. We've removed the liquid cooling connections. We've removed the cooling and reduced the fan size. We have a version without a fan. We simplified the FPGA and onboard processing. We've reduced the size 60%. We maintained 0.8 electrons of read noise. We kept the image quality. We got the patterns under control. We kept the triggering functions. We've traded things like speed. We don't do 300 frames a second. We do 140, and we have a version that just does, I think, 45. We've traded a little bit of QE. We have an exclusive 83% peak QE sensor in this camera. And we've traded dark current because we don't have the cooling at the same levels. We've traded because industrial thoughts, integration into a system might not need everything we're giving the research scientist who needs that cutting edge, incredibly low read noise. And we can see, look, it's smaller. It fits into an instrument easier. It's cheaper. These things are out there as well. But this is designed for people putting them inside instruments who want to buy hundreds of them and have smaller instrument size so it fits onto a desktop. People want these things on benches, right? They don't want to have these large machines like semiconductor inspection machines. They want a benchtop machine that gives me an answer quickly and easily. So this is the basic specs of it. It's a rolling shutter. It's using a 6.5 micron pixel. It's got an 83% QE sensor. This version is a 5 gigabit. So this has got fins on it, so no active cooling, and it's USB 5 gigabit 3.2. So it's a nice little camera. It's an exclusive sensor. We have a 10 gigabit version as well. This does 140 frames a second. And that's because it's got USB 3.2 and coax express on it. So we have that, and we have a fan with it as well, because we want to maintain a little bit of heat removal on this because we're going faster. And I said going faster gives you heat. And we got a nice little sensor. You can see here, it kind of compares really nicely to existing sensors in the market. This is an exclusive to us. And that's it. It's a pretty cool little camera, the Aries 65A4 LT. And we'll be putting that onto the website really, really soon. It is a smaller, more versatile, lower cost package for people integrating into systems. If you're a research scientist, buy the Pro version. It's the best camera in the world. Then we got this little guy. This little guy is great. Some of the people on this have had these little guys. This is great. So you wanted smaller, we give you smaller. It's not the same. It's not the same as a 6.5. We haven't made the same one smaller. But what we got here is a 3.4, 12 million pixel sensor in a very tiny little body, right? It's 17.4 millimeter diagonal. So 18.8 is your normal kind of like sCMOS sensor, your 2K. We're a little bit in. Not the end of the world. It's got 1.35 electrons of read noise. It's got 75% QE. It's a global shutter, which is great for timing. It does 18 frames a second in 12-bit. This camera is like, I don't know, $2,000 or something, right? In a world where this would outperform when we had it, the CoolSnap HQ2, not for staring, but for most imaging. Look, 75%, 1.3 electrons. Awesome, 18 frames a second USB. Great little camera. So what's our smallest camera that we've got? Yeah, great little, simple, nice, wide. You know, everyone wants a QE curve that does that. It's nearly there. So we've got that. What else have we got? Well, we've got these cameras. These are TDI cameras. And we're doing some webinars in the future about how TDI works and so on. We've also got some webinars that exist for it. But let me tell you, we have this 8K TDI camera, this Gemini 8K TDI, back illuminated 95%, whatever it is, QE, all the way across. This is the fastest, lowest noise TDI sCMOS camera. 4 electrons, which is pretty awesome at this level, running in its highest gain modes. Got this great camera. And then what we can do is we go ahead and we reduce it. The same thing, we've reduced the size of the camera and we simplified the camera for customers who don't need it at this level. We have customers that use both of these on one system. We just made the same thing. We removed the liquid cooling option. There is going to be one come in. We've removed and reduced the fan size. We've simplified the FPGA. We've reduced the size by 69%. We've maintained this 4.5 electron, I think it's 4.1 actually, but 3.9 actually, I think we're in 256 stages. We kept the high quality. We kept the triggering functions. We've got all of that, but we traded speed. This isn't 1 megahertz, this is 500 kilohertz. It's still 500,000 lines a second. That's still pretty phenomenal. And the dark current performance is awesome, right? Awesome. The dark current performance is reduced. The dark current on the 8K TDI is wonderful. The Gemini 8K is awesome. But the 8K TDI is perfectly fine. But again, if you're doing any science with TDI, you've got to be careful. And that's why we've got 3 different versions. We've got a passively cooled one for anyone who's looking to use an industrial, like the industrial guys have TDI. We've got a fan cooled one for people starting to do it and saying, well, actually, we need to have some cooling on it. We want to remove the heat. And we have a liquid one that's in development. We could, if anyone wants it, we could pull it out in 3 months if we needed to, but we'll probably launch it around November. Anyway, awesome. 3 new smaller 8K family members coming into this based on the 8K TDI sensor. There we go. Oh, a little bit of a graphic. And we can see here we've got 2 different versions of sensors. We have a UV version for anyone doing semiconductor inspection, because you guys kind of like that. And then we have a visible one for people that want to work with cells, because I've looked into it and they don't like UV light. So we've got 2 different versions of the sensor here, 3 different versions of cameras for the LT version, and we have the main 8K TDI as well. So let's get back to our thinking here. Let's get back to it. We know that we've got these industrial cameras. We know that they're looking at different light levels. We know that there are different challenges. I don't want to get you wrong. They all do an awesome job. And if you have the light and you have the conditions, go ahead and use cameras like that. And we know we have scientific cameras. We tend to have different use cases for them. They are looking at different light levels. And when there are different light levels, there are different problems. And therefore, we're trying to concentrate on what those different cameras, those problems are, to fix them and minimize them and make the imaging as best as they can. Because these cameras are about measuring things. And what's in between them? We believe that there is these industrial scientific cameras in between them. And these are just a few of the ones that we have at Tucsen. We concentrate on these challenging inspection and advanced research. That's pretty much what we say in the strapline. So, thank you. There we are. I don't know which time zone I am on, but I have finished for the day. Well, I have to do this again at about 8 o'clock my time. But if anyone's got any questions, I'm going to hang on until you all do. And then I have what is now a relatively cold cup of tea and then maybe a Red Bull. We'll see how it goes. I'm joking. I'm not putting that mess in my body. I want water and tea and coffee are about as bad as I can. So hopefully you're still with me. You've had the little break. I think for now, we'll wait. If I see any questions in the next 15 seconds, we'll stay on. If not, we'll say thank you. And I will take any questions. You can DM me, I believe the kids call it, or you can email me, or whatever you would like. You're welcome to talk to us at any time, apart from on the weekend, because I'm tired. Thank you, Reese. Everyone else, it's the weekend. If you're watching this in Europe, Central Europe, it's what, 20 minutes to 4 in the afternoon. Pretty sure that's got beer written on it, or sloping off early if you haven't done so already. A touch of the Fridays, I believe they call it. Poets' Day. Something off early, tomorrow's Saturday. What's the best camera for semi-wafer inspections? It depends. Most people, Dan, use TDI cameras if they're wanting to inspect at speed. We get people wanting different things. Some people will use SWIR cameras. We have SWIR cameras coming. It totally depends. But most of the time, the job is, can I inspect that wafer at the highest possible speed and get the job done as fast as possible? And normally, TDI is doing that. If you want to have a chat with it, we're really interested in inspecting it. We're one of the most dominant players in semiconductor in Asia. And we really want to grow what we're doing outside of Asia with it. We have a few customers in the Bay Area, but we're looking for more and more semiconductor inspection jobs. We have a few in Europe as well, but we're looking for more. That'd be my phone. Perfect. I'm going to take it if everything's good there. Hopefully all's good. And I'm going to say have a good weekend to everyone. And I will catch up with you later on. Thank you very much, everyone. I hope you enjoyed it. I will speak later on. Bye now.